Welcome to our advanced masterclass on Module 3, where we explore emerging carbon capture and storage technologies. In this video, we will analyze next-generation solid sorbents, electrochemical systems, subsea clathrate thermodynamics, and the CO2-CH4 exchange process. In this first part, we examine the shifting horizons of capture technology, moving beyond traditional methods to more efficient, sustainable solutions. Traditional liquid amine systems face significant hurdles. They carry a heavy thermal penalty, requiring massive energy to boil water and break bonds. Additionally, their environmental footprint is a concern due to oxidative degradation, which produces volatile compounds and complicates safety management. To overcome these limitations, we are seeing a shift toward an emerging tech frontier. This includes gas hydrates, which trap carbon dioxide physically using high-pressure water cages, solid sorbents like MOFs that offer selective sorting, and electrochemical methods that use green electricity to bypass thermal regeneration. Moving to Part 2, we take a closer look at the science and application of clathrate gas hydrates. Gas hydrates are crystalline solids formed from hydrogen-bonded water cages. In a hydrate-based capture process, carbon dioxide is selectively trapped within these cages under high pressure, providing a physical separation method that functions without the need for toxic chemical solvents. The configuration of these water cages depends on the gas molecules being trapped. Structure I forms cubic geometries for CO2 and methane, while Structure 2 accommodates larger molecules. Structure H is a hexagonal configuration used for even larger organic molecules. Thermodynamic equilibrium is critical here. CO2 hydrate stability depends on specific temperature and pressure conditions. A major focus of current engineering research is lowering the pressure threshold, currently over 30 bars at 2 degrees Celsius, to reduce the compression burden on industrial processes. Chemical promoters can greatly improve efficiency. Thermodynamic promoters like THF stabilize cages to reduce pressure requirements. Kinetic promoters, such as surfactants, accelerate crystal growth rates. Additionally, researchers are developing green, non-toxic alternatives like amino acids to replace traditional industrial surfactants. The process loop for hydrate capture involves two main phases: crystallization and dissociation. In the first, CO2 is trapped in a cooled reactor while other gases are vented. In the second, the slurry is moved to a lower pressure separator, where slight warming releases pure CO2 and recovers water for recycling. Subsea sequestration offers a dual benefit approach. By injecting liquid CO2 into deep-sea methane hydrate deposits, we trigger a natural molecular swap. The CO2 forms more stable hydrate structures, effectively locking it away permanently while allowing the methane to be recovered. Part 3 focuses on solid sorbents, with a specific look at the potential of metal organic frameworks, or MOFs. MOFs are highly engineered, porous crystalline materials. They offer exceptional surface area, with just a single gram potentially covering the area of a football field. Their pore chemistry is tunable, allowing them to be designed to specifically target carbon dioxide and require less heat for regeneration. Adsorption occurs via two main mechanisms: physisorption and chemisorption. Physisorption relies on weak physical forces, making it energy efficient but less selective. Chemisorption uses stronger chemical bonds, which increases selectivity for dilute gas streams, though it requires slightly more energy to regenerate. Ultimately, the transition from liquid amines to dry, porous solid sorbents is transformative. By eliminating the need to heat massive volumes of water, these systems can reduce the total thermal energy required for regeneration by up to 60%, significantly improving overall plant efficiency. This performance matrix compares various sorbent classes. Zeolites, activated carbon, amine-grafted silicas, and MOFs offer different trade-offs in CO2 capacity, selectivity, moisture tolerance, and regeneration temperature. Selecting the right material is essential for optimizing capture performance in specific industrial conditions. In Part 4, we explore electrochemical capture and membrane separation technologies, both of which offer innovative pathways for industrial decarbonization. Electrochemical capture uses electric fields to control the process. Charge swing alters the molecular state of a sorbent, while pH swing uses electrolysis to drive CO2 absorption or release. These systems are highly compatible with renewable energy, enabling direct integration with green power grids and removing the need for thermal loops. Membrane separation technology is also evolving. Polymer gas sieves provide a reliable, passive method to filter CO2 from nitrogen. Meanwhile, facilitated transport membranes use embedded chemical carriers to selectively ferry CO2 across the barrier, providing high selectivity even for dilute flue gas, provided the environment is kept dust-free. Finally, Part 5 covers chemical looping and the broader economic considerations of deploying these emerging technologies at scale. Chemical looping combustion uses metal oxide oxygen carriers to transfer oxygen directly to the fuel. Because this occurs without atmospheric nitrogen, the exhaust consists primarily of CO2 and water vapor. This leads to a simplified recovery process, as condensing the water leaves behind a high-purity CO2 stream, completely bypassing traditional solvent loops. Ultimately, these technologies are aimed at reducing the thermodynamic energy penalty of capture. By lowering these barriers, we can substantially cut the long-term operating costs of industrial plants, making large-scale carbon capture both technically feasible and economically attractive over the coming decade. However, scale-up presents challenges. Synthesizing advanced materials like MOFs and specialized membranes in industrial volumes remains complex and costly. Additionally, industrial flue gases contain contaminants that can cause degradation, requiring the development of highly robust materials to ensure long-term operational success. Current technology readiness levels vary. Solid sorbents and membranes are reaching TRL 7 to 9, nearing full commercial deployment. More advanced concepts like electrochemical capture and hydrate-based systems are currently at TRL 3 to 6 as they transition from lab research into early-stage field trials. This concludes our module on emerging CCUS technologies. Thank you for your time and participation in this professional training course. Please reach out if you have further questions. For those interested in further collaboration on research, prototype design, or technical training, please see the contact details on screen. We look forward to advancing these critical solutions together.